Okay, good morning. Today is June 12th, and we're July, I'm sorry, July 12th, and we're going to continue with our material after this 1 week break with the evaluations. The evaluation is ready, so probably today I will send the results, the feedback, your comments to your two problems. And one question, did you receive your own results for the first part of the evaluation? Did you receive, do you know already how many questions you answered correctly in the first part of the evaluation?
Yes, doctor.
Oh, so you have it already, good. And then today I will ask the assistants to send you the results of the evaluation of the two problems that you have to solve. Okay. Today I would like to go over that and see what we have learned in that respect. Okay. Then I would like to start the new chapter on plates. Okay. It's going to be something. It's going to bring some new things. Okay. Especially the fact that up to now, basically, we have one variable, okay, x, okay? So you have to determine the distribution of shear force, bending moment, and so on in x. In the y direction, in the vertical direction, we assume that we could approximate the stress distribution using the kinematic hypothesis. Okay, in the z direction, there was no variation, except when we start talking about effective breadth. So now we have influence from both x and y. Okay, so all derivatives will be partial. So we have to be aware of that. Okay, and the two problems in x and y, they will be coupled. Okay, and for that, we have to include in our analysis the Hooke's law, but including both sigma x, sigma y. We will review this in a minute, okay? At the end, I'm going to give you a couple of instructions. We have some plans for this Friday, right, Isaac? Everything is ready for this Friday?
Yes,
some of you came last week to get everything ready for that, so we're ready for completing some lab work. It's not obligatory since it is out of the original plan, but we need some of you to come to perform the test. Okay, so we will talk about that at the end. Okay, so let's go on. I have here the results, and let's show the. Let's share the. Yeah. Can you see the evaluation?
Yes.
Okay. So thank you, Mr. Nieto. Can you read the first problem, please? Can you read the first problem?
Okay, doctor. In a beam built from a steel flat bar with P and thickness T, seated on the sides of the thickness, it is applied shear force. If the yield point in shear of the material is 115
Megapascals.
megapascal, deduce an expression for the maximum force that might be applied on the section, calling A the total area of the section.
What's the translation for flat bar, Mr. Nieto? Do you remember the translation in Spanish for flat bar? Would you please turn on your cameras if possible, people? So, because for this part, I would like to do some interaction. Okay, so I would like to see who am I talking to. Mr. Nieto, do you remember the translation for flat bar?
I don't remember, doctor.
Oh, come on. Then how did you answer this question if you didn't know? Do you know what a flat bar is? Mr. Nieto, do you remember what a flat bar is?
The flag bar.
Yeah, what is it? Do you know what a flat bar is?
Mm,
Mr. Zurita, do you have anything surrounding around you that you can share with us, showing what a flat bar is?
Good morning, doctor. Flash bar.
Miss Jurado, do you have something that can explain what a flat bar is?
Good morning, doctor. Yes, it's something like this, just this part.
Exactly. So it's
It's a
the section,
platinum.
the section is a rectangle, okay? Just like this, okay? So the section is a rectangle. It's very long, and that's it. That's a flat bar. Okay, it's sitting on this side, like this. Okay, because you have a flat bar, you can analyze it like this or like this. So, I mean, if I didn't write this, seated on the side of the thickness, okay, this is the thickness. So it's telling you that it is like this because it's seated like this. Okay, Mr. Nieto? So, how do you calculate, Mr. Nieto, how do you calculate the maximum force that may be applied on this section? Mr. Nieto, how do you calculate, how do you answer this question?
I don't know, doctor.
No, okay, no problem, no problem. We're trying to, okay, Miss Acuña is here. Is Miss Acuña here?
Yes, doctor.
Sí,
Good morning.
so, good morning. How can you answer this question?
I don't know. In the exam, I get this wrong.
Yeah, but that's what I'm asking you.
How do you say despejar?
Take out.
Take out for the formula of the shear stress.
What's the formula for
the shear
stress?
force
Exactly, that's it. What's the formula for the shear stress?
is the shear stress. No, the shear force.
Okay.
Multiplied by the first moment of the area.
Not of the area,
No.
of the sector. Of
The sector.
Okay.
The sector divided by the inertia multiplied by the thickness.
Okay, yes, at the point of the cut. Yes, yeah, that's it. And Miss Acuña, I don't want to bother you, but what was the problem? Why you couldn't answer this question?
I think is that I consider wrong the sector because my result is the option C, but I think is wrong. Because
Yeah, but the thing is this, okay, you define it correctly, okay, that's the formula that we have deduced to calculate the shear stress. And we are assigning the maximum value of the shear stress. The point is, where is that maximum value? Where does this maximum value occur in a section? Let me go with somebody else. Mr. Aizaga. Is Mr. Aizaga here?
Yes, doctor, I'm here.
Okay, where is in the section? What in the section takes place the maximum value of the shear stress?
In the middle of the flat bar.
No, we have a special name for that.
Mm,
What's the name of that in the middle of that? We didn't call it like that. Oh, Miss Avilés, how do you call the middle, as Mr. Ezaga says? Miss Avilés?
Good morning, doctor. The middle of the flat bar, the
what?
section.
The what?
It's the middle section.
No. The middle section is when you see in the other direction, in the x-axis, yes, then you call it midships. But I'm looking at the section.
Línea de crujía.
No.
The half height.
Yeah, but how do you call that?
Neutral axis, doctor.
Exactly, neutral axis. Neutral axis, yes. On the neutral axis, you have the maximum shear stress. Good. Now, let's go on. Mr. Vanegas is here. Is here, Mr. Vanegas? Mr. Vanegas? No?
No.
Okay. Okay, Mr. Vanegas, do you remember how to evaluate the maximum value of the first moment, big Q? How to evaluate the big Q for the flat bar? Mr. Vanegas, do you remember how to calculate the maximum value of Q for the flat bar? Mr. Vanegas, can you hear me? I see that can you turn on everybody please turn on your cameras. I don't want to talk myself, please. Mr. Vanegas, can you talk? No? Okay, let me go to somebody else. Mr. Benavides? Benavides is here, Benavides?
Good morning, doctor.
Hello.
We can calculate that is the area of the section times the position of the centroid.
Come on, but give me
Well,
correctly. Give me a value of Q.
The value of Q for this case, if we consider that is the T times B and a half, that is the area, and the position of the centroid is
Yeah, but
B.
see, just a second, Mr. Benavides. See, we have employed this formula so many times. Okay, we have employed this so many times. This is something that should be in here, right?
Yeah.
Yeah, I mean it's okay. So, Mr. Carranza, what is the maximum value of Q in a flat bar section? Mr. Carranza, are you there?
Yes, doctor, good morning. The maximum value is in the neutral axis. In this case,
Please listen to the question. I'm not asking where, I'm asking how much is the value.
P squared T is T multiplies thickness divide H. In this case.
Is this correct? Mr. Cedeño Carrillo, is this correct? Mr. Cedeño? Cedeño Carrillo is here? No? Mr. Cedeño Parra? Mr. Cedeño Parra? Is correct what Mr. Carranza said?
I think it's correct, doctor.
That's something that we should have in our mind. I mean, we have employed this formula so many times for the rectangular section. So it's
Doctor,
P
over
2.
there, I have a question.
Yeah, go on.
Because I understood that the maximum force that may be applied is when the material doesn't breaks or doesn't fail.
Doesn't reach the yield point, because remember, One
Or does
thing
not
is
fail.
the yield point, another thing is the maximum stress, ultimate stress. In this case, clearly we are talking about the yield point. Go on.
And yeah, and I apply the formula for tau allowable, that is equal to the tau yielding divided by safety factors. And then I obtain the tau allowable and then separate by the formula of shear force divided by the area, and I obtain the C, the letter C.
Yeah. Yeah, but the problem with that is that we tell you that the shear is the maximum. If you evaluate if you do a test, okay, if you do a test, I see your point. If you evaluate, I'm sorry, if you make a test, right, and measure the yield point in a real specimen, steel specimen, the value will be higher than 115. So if I give you 115, it includes the safety factor already. But I see your point. I see your point. Is there any other questions about this? Any other
Doctor,
question?
I did the same in the first exercise of the theoretical part, and I think that other classmates did the same.
Okay. Okay, I'll have to review that then. Yeah, and I'll consider that. What I did was I made a mistake when I did the test, because instead of divided, it was supposed to be multiplied by. But I don't know, I typed it incorrectly. Yeah, okay, I'll give you credit for that. But and then I will have to review that after class.
Doctor,
Okay.
but in my correction, I did the procedure that you tell us, and with the formula of the shear stress in the neutral axis, and I obtained the first A.
I know.
The answer A. Yes.
Yeah, that's I think that's the correct one. Especially what I said, right? When you do a test, you don't get 115 megapascals for the yield point. You get something higher than that. And what you do is you subtract a little bit in order to be on the safe. So you are already considering a safety factor. Yeah. But yeah, it can be considered also a correct one, the option C. And I will give you credit for that too. Okay. But I'll have to review. Okay, let's go to, oh man, it's 7:30. So I have time only until 8. Let's go to the second question. Let's see, ask somebody to read it. Mr. Chikaisa, can you read it, please? The second question. Mr. Chikaisa, are you there? Mr. Chinchin?
Yes, doctor. Good morning. Number 2. After calculate the bending to a lateral load of the combination.
Mr. Chinchin, it says after calculating. Okay, please try to go on.
After calculating the bending to a lateral load of the combination of a vertical stiffener welded to a horizontal plate, the following stress distribution with trapezoidal shape is obtained.
Okay, so this is the distribution of the normal stress on the flange. It has a trapezoidal shape. Go on.
Calculate the effectiveness of the flange, considering that the material is steel, thickness 8 millimeters, B 30 centimeters, B1 20 centimeters, H 70 centimeters, and sigma x1 100 and sigma x2 150 Newton over millimeter squared.
Okay, so how did you solve this problem, Mr. Chin Chin?
First, calculate the area of the normal stress.
Okay. And then?
Divided by the sigma max.
Yeah.
And
What's the value of the
finally,
sigma max?
sigma max 150 Newton over millimeter square.
Yeah. Okay, thank you. Thank you. Mr. Chiriboga, are you here?
Yes, doctor, good morning.
What can you say about this problem? Did you get any confusion about the information or? Mr. Chiriboga?
I didn't this problem.
Yeah, that's what I'm asking. That's what I'm asking. That's the reason I'm asking you. Did you solve these quiz? Did you complete the solution for this?
For the homework, yes, but I don't know is okay.
Oh man, we're in trouble here. Dominguez Tumbaco, good morning.
Good morning, doctor.
Did you have any problems with this problem? Did you, I mean, you get confused or something?
No, doctor, my solution is the same of the Mr. Chin Chin.
I'm sorry, I was reading that wrong. Yeah, you're right. But in the test, you didn't do correctly, Dominguez.
Yes, because I take the normal stress, correction normal stress. Yes,
Yeah,
I think this moment I thought.
Yeah, but the problem, see, what I'm trying to understand is if it was clear, I mean, what was the problem? That's what I'm trying to determine here.
In my case, doctor,
Just a second, please. Let me go first with somebody and then I will change to somebody else.
Okay.
Okay. Ms. Dominguez?
Yes, doctor.
Why you didn't correctly? I mean, you misunderstood something or anything else?
And when I in the quiz, I thought the normal correction stress, it was 100 because it's in the position normal stress x1 in the graphic of the Shipstruck notes. It was there.
Okay. Flores. Is Flores? Any comment on this problem?
No, doctor.
And did you solve it now? Did you prepare the solution?
No, but yesterday I tried to solve it.
And
I can do that.
You cannot, or you did?
Yeah, I did.
Okay. And so what was the problem during the test?
I use an incorrect value above the normal stress.
Okay.
Mm.
But the reason for that was because it wasn't clear or something else?
I think it was because I have some nervous.
Mhm, yeah. Okay. Okay. Good. So as Mr. Chinchin explained, what you have to do, you have to integrate this stress multiplied by the area. And it was easy because the shape of the distribution was simplified. I was going to give you a curve, right? Curvilinear distribution, but it was going to be difficult for you to get the same answer. So that's why I decided to give you this simplified distribution. Okay, and then just divide it by the maximum value, which was 150. There was a question from somebody. There was a question. Anybody was going to ask me something? Now it's the time to ask. No? Okay. Let's go to the third question. Mr. Gomez Gamba, would you please read it?
Good morning, doctor.
Would you please read it? Read problem 3. Can you read, Mr. Gomez?
Yes. I read.
Yeah, problem 3.
Problem 3. Protocol of statement with one is true. A unit of the potential work that may be developed by external force are M L over T squared. B, the work developed by the external force is a function which can take only positive values. C, the strain energy can have a positive or negative value. D, in bending, if the normal stress is negative, the strain energy is also negative.
Okay. Answer the question, Mr. Gomez.
Letter A. The unit are it.
Okay. Let's go on. Thank you, Mr. Guaman. What's wrong with the option B, Mr. Guaman? What's wrong with option B?
That the external force could be positive or negative too. We don't have only positive.
Yes, exactly. You have a beam, for example, you have a force pointing downward, but you have something else here, it can move there. So in this case, the force doesn't move in this direction, but moves upward. So yeah, you can have positive or negative value for the external work. Okay, thank you, Mr. Guaman. Mr. Hidrobo, what's wrong with option C? Mr. Hidrobo, what's wrong with option C?
The strain energy just only can be positive?
Yes, yes. Strain energy is just positive. I mean, you have a beam and you deform it upward, so it stores energy. If it deforms downward, it stores energy. That's something that we insisted in class. Strain energy has to be positive all the time. Okay? And remember, when you calculated for a beam, you said it's equal to what? The moment squared. when you square something, you automatically get some positive values, right? If you divide it by E I sub C, E is always positive. It's not Emelec, it's Young modulus. Young modulus is always positive. And the inertia, people, inertia is always positive. It's Y squared. So when you square something, you get positive. And dA, the differential of an area, is always positive. This is not Star Wars. And in Star Wars, yes, you got negative areas, anti-masses, and something like that. No. Here, mass is positive. Area is positive. So U is always positive. Yes. Thank you. Thank you, Mr. Hidalgo.
Doctor,
Yes.
excuse me. But
who is speaking? I don't see who's speaking.
Raul Pesantes. I am.
Go on. Go on.
Okay. In this question, in the aula virtual, the dimension of the external forces, in my case, I can see M times L over T times 2, no square.
Did anybody have the same problem? Anybody had the same problem? Let me write down. Okay, so I'll have to go in the aula virtual and check. I'll try to do this, believe me, but it's a problem with the characters. Yes, let me write down. Okay, then just a second. Where's my pen?
Yes, doctor.
Yeah, you're Mr. Pesantes. Pesantes, right?
Yes.
It was a mistake. I see the same that Pesantes at the exam.
But the problem was that there was none of them, the other were correct, definitely. So there's not much option there.
Yeah,
because
I confused with the external force, so I didn't do well.
Okay, I'd have it there, so I'll review it later. We were by Ms. Jimenez. Ms. Jimenez, what's wrong with option D? Ms.
The
Jimenez?
strong energy cannot be negative.
Yes, yes. So option D is similar to option C. No matter what the sign of the stress is, right? Remember, if you go back when we started chapter 3, we said the integral of sigma squared over E times dV, that's internal strain energy. So even if sigma x is negative, you have to square it to calculate EU. So, and then it becomes positive. So there was no chance. I mean, the only chance was that the first one was this. Okay, let's go to the last one, 4. Somebody, Ms. Jurado, would you please read question 4?
Yes, doctor. Applying an energy method, calculate the slope of the end of the clamped beam with a concentrated moment on the right end. The options 2 or no?
Yeah. So we have 4 options. Which one did you choose?
Yeah.
It's difficult because it's difficult to recognize all of this in here, but yeah. How did you solve it, Ms. Jurado? How did you solve it?
First, I see the boundary conditions of this beam and then I do the equation, but I will be
how is
confused.
the, see, in this case, see, even though I was asking you to apply an energy method,
Yeah.
you could have solved this solving the differential equation.
Yeah.
I was not looking at your paper. So the only thing that you have to do is you have to pick. So if you solve this problem, solving the differential equation of equilibrium of a beam, if you could get the correct answer, yes, you could do it. Because I was not looking at you. Is this a determinate case, Ms. Jurado?
Yes, doctor.
Yes, it is. What are the unknowns here?
Excuse me?
What are the unknowns here? What unknowns here do you have? Okay, no problem. Let me go to somebody, don't worry. Miss Leon, Miss Leon. Miss Leon, can you hear me?
Yes, good morning. Good morning, doctor.
Oh.
Yes.
Would you please turn on your camera if possible? Because I don't want to see.
Yes.
If
no
possible,
problem.
if possible. Okay, I understand there are some private situations. If it's possible, yeah. Okay, go on. So Ms. Jurado said that this is a statically determinate case.
Yes.
My question is, okay, how many reactions do you have here that you don't know? That you try to
I have
determine?
the,
How many
the
reactions?
reaction in A and moment in A.
Remember that when we talk about reactions, that's a general name. It could be force or it could be moment. When you say reaction, you mean what? Force or moment?
There is a reaction in the plant
Yeah,
side.
I know. But my question is, when you say reaction, that could mean, you could mean either force or you could mean moment.
It's a
this case, my question is, the reaction here is a force or is a moment?
It will be a force.
With
And
force?
And you also have a moment.
What happened? I mean, can you rotate the left side, the left end? Can rotate?
No, you can rotate, but you have
No,
right there.
you cannot rotate. The left end cannot rotate. It's clapping.
But the other side can rotate.
Yeah, but I'm asking is on what the reaction. So the left-hand side cannot move, cannot rotate. If cannot move, you have to develop a force. And cannot rotate, you have to develop a moment.
Okay.
So on the clamped end, you have two reactions, force and moment.
Yes.
So two unknowns. And how many equations do you have here? Let me go to somebody else. Mr. Llanos, how many equations do you have here to calculate the reactions? Mr. Llanos? No? Mr. Medina? Mr. Medina? No? Mr. Mendez?
Yes, doctor.
How many equations do you have here to find these reactions?
Two equations.
Yes. What are those equations?
Moment and force.
Summation of moments and summation of forces. Yes. Okay, now, if we talk about the differential equation, what's the differential equation that we should solve in this case, since it is a determinate case? Let's go to the next one. Mr. Miño. Is here Mr. Miño? No? Mr. Ortega? What's the equilibrium equation, Mr. Ortega?
Yes, doctor. Good morning.
What's the differential equation?
EI, the second
No,
derivative.
no. Remember, this is a determinate case. We're talking about equilibrium only.
The second derivative is the moment is pdx.
Exactly. It's equal to px. How much is p of x in this case? What is p of x in this case? No?
N sub 0.
Exactly. There's nothing. There is nothing. So the second derivative of the moment is equal to 0. Yes. So the moment is either a linear variation or a constant. Okay. How many forces do we have in this case? Let's go next one. Mr. Paredes Castillo, how many forces do we have in this case? In general, external forces in this case, how many external forces do you have in this case? Mr. Paredes Castillo? No? Mr. Paredes Montoya?
Constant is the shear force.
And
The
how much
external-
is that? How much is the shear force in this case?
In this case, sería in the moment for length.
Oh man, we're having trouble with understanding each other now. My question is, how many vertical forces do you have in this case? How many?
0.
You have one because you have a reaction on here, right? Because you have a clampet on the left-hand side.
Yes, but in coupling reaction in the moment, in the force, in the moment, no composed, in the moment the coupling.
Yeah, but you have a reaction. The problem is that if you have one single force, right? Only one force, and you are in equilibrium, right? Well, what is the value of that force to be in equilibrium? In general, if you have one force and you have another one here, they can cancel each other. But if you have one single force, you are in trouble. How much has to be this force equal to if you want the system to be in equilibrium in the vertical direction? Anybody? You have a beam, you have a clamp end, you have a reaction, and you have a reaction. This force here is the only one that you have in the system. How much is this force has to be?
Zero.
Exactly.
0.
It has to be 0 because there is one single force. And if you need it to be in equilibrium, that force has to be 0. So there is no shear force. If the shear force is 0, then the bending moment is constant. See?
Yes.
It's just a matter of thinking. Okay, let's go on. 6 minutes only. Oh man, let's see. Mr. Pesantes, can you read it, please?
Doctor.
Okay.
Just a second. There is a question. There is a question from somebody.
Sorry for the interruption. In that question, yes. My answer is D. But in Aula Virtual, I had my answer bad. So I put my
What are the units of the numerator here?
The units.
What are the units of the numerator?
The numerator force length squared.
Cube.
The
Force length cubed. Now, what are the units of the denominator?
Denominator is force over, no. My answer is D.
Por length square sería.
Yeah.
Denominator.
So This cannot, these two, B or C cannot be because the units are incorrect.
No, doctor. D.
E?
D.
Okay, but what you can do is you can solve it numerically, analytically.
Is I put my answer with my procedure in the correction. And my question is if you can review, maybe.
You can solve it analytically. There is no need to do anything. I mean, you can solve it analytically. And you get the answer.
The correct answer is A.
Yeah. Yeah. Because in the second moment, I don't know if I can write here. I cannot write here. Change, I guess. Okay, we're saying is that the bending moment is equal to M0. This is a constant, and it's equal to EI P comma XX, right? So you integrate once, and you say M0X plus A is equal to EI P comma X. So at 0, because it's clamped, P comma X at 0 is 0. So this is 0. So this is theta at L, at X. If you evaluate this at L, you get theta at L is equal to M0 L divided by EI. Is that less?
Yes,
Yeah,
doctor,
you can
but
review that later. Let me go at least a little bit with this problem because
that is an analytical solution, but the problem said applying an energy method.
yeah, but I mean, if you apply the energy method, you should get the same. So you have to apply U. So U would be 1/2 M0 squared L, and the work would be M0 times the slope 1/2. Make them equal, and you get it. U is equal to W. Miss Agnes?
Yes, doctor.
Okay. Okay. Did I ask somebody to read it? Mr. Pesantes, please read problem 1.
Yes, doctor. Okay, after completing the analysis of the steel barge, which has one longitudinal bulkhead height located at the center line. It was determined the shear stress on the deck at the connection with the side is 27.9 megapascal. The shear forces applied on the section is 5 meganewton. The section has an inertia of 1.67 meters 4, and the vertical position of the neutral axis is 2.58 meters from the bottom. Determine the point on the deck measured from the corner B, where the shear stress is null.
Okay. Oh man, I cannot write on here. Is there any way I can write here, people? Do you know if I can write? Oh, I think I can write now. Okay, so here, the stress is 27.9, right? Because it says that the stress on the deck, okay, this is the deck. In the connection with the side, this is the side. Did anybody have problems with that information? Mr. Pesantes, is this what you understood?
No. In
No?
this case, I
Okay.
confused the result.
Okay, so we're clear. This is the deck, this is the side. The information says that the shear stress on the deck, so this is the deck, this is the deck. And the connection with the side, this is the side. So here the stress is 27.9. Now, what's the neutral axis is about here. There. Now, in this situation, okay, I'm measuring in this direction, I measure Y. In this direction, I measure Z. And coming out of the graph, I have X, right? So it's X, Y, Z. X, Y, Z. What's the distribution of the stress on the deck? Let me ask someone. Miss Poveda, what's the shape that has the shear stress distribution on the deck or on the flange of the beam? Miss Poveda, can you hear me? Are you here? Miss Poveda, are you here? No. Oh. Poveda is not here. Ask somebody. Miss Puertas, are you here? Miss Puertas, are you here?
Good morning.
Good morning. What's the distribution of shear stress on the deck? One word. One word. What is the distribution? What is the shape, the mathematical function that describes the distribution of the shear stress? Miss Puertas.
Just a bending moment. Is the moment?
What's the distribution? So do you remember the distribution in this case, for example? Okay. What was the distribution of shear stress on the deck?
In the neutral axis.
No, the distribution on the deck here.
Like in the deck.
Yes. If you make cuts at different points, so at different cuts, different values, what's the distribution? Do you don't remember? Let me ask somebody. Who's next? Mr. Kimi, Andres Kimi. What's the distribution on the deck or on the flange? Mr. Kimi, Andres Kimi, are you here? No. Mr. Kimi Moran, are you here? Mr. Kimi? Oh man. Anybody? What's the distribution of a shear stress on the deck?
Linearly.
One word.
Linear.
Linear.
Linear,
Linearly,
yes, linear. So if I have a value here, I'm going to have a linear distribution. If I do an analysis, what's happening is this, okay? Let me erase that because that's not a straight line. Okay, so if I do a cut, okay, on this side here, there is no stress. On this side here, I have 27.9. So it's going to be like this. So this value here is 27.9. Now on this side, I have a force in the X direction and another force in the X direction like this. That's the situation. That's the situation. So this is the sector that I'm considering. Okay, now, if I do this, this is my sector, then I can say that tau at here, because that's where I start the sector. I integrate from here until here. Why until here? Because here I know that the shear stress is 0. And that's equal to VQ at B divided by inertia and B. But please, this is not equal to 0. Because this is the beginning of my sector. When I do this, okay, this is a flat bar, okay? And I say, okay, I'm going to start here. This is my sector. And here is the value that I calculate. And here, tau is 0. Similar. From here, you calculate Q, and from Q, you calculate the distance from here to there. Now, if I need the maximum shear stress, okay, obviously it's going to be here. That's the second part. Now, I know that the shear stress here is 0. By symmetry, shear stress 0 is here. So this is now my sector. Let me change color for the second part. So for the second part, this is my sector. So I cut here. Where I know that the value is max. And I consider all of this area. And here, similarly as is in this point, in these 2 points, the shear stress is 0. So I have one equation, which is this one, to obtain the value here. So to calculate Q, I need to consider this part and this part. Okay, people, let's go to a break. Unfortunately, we had no time to talk about the last problem. I hope that this helps you, okay? Let's have a 5-minute break, and when we come back, we will go with chapter 4, okay? Is there any final question? Any final questions about this? No final questions? Okay, so let's go to a break. Isaac,